Welcome to the FET magnets and electromagnets simulation. If you couldn't get this sim to work on your computer, then you can follow along with this screencast and fill out your worksheet this way. Hopefully you will have completed question 1 through 9 already on your worksheet using the reading to find those answers. And we'll jump right in with question number 10. It says, first move the compass slowly around the bar magnet. So I'm just going to grab onto the magnet here and notice what happens to the needle as we move the compass around the magnet. Remember that the needle of the compass has been magnetized. It's a ferromagnetic material. And so the first question says, which pole of the magnet does the red compass needle point towards? So here we have it right at the south end of the magnet, and we see that it's attracting the red half of the compass needle. Now I'm going to flip the polarity here, which is just going to swap the north and south ends of the magnet, and notice what happens to the compass. The compass needle changes as well. So number 11 asks, now which pole of the magnet does the red compass needle point to? And I'll just move this around here again, and you'll see that the red half of the compass needle still is attracted to the south end of the magnet. So number 12, this means that the red part of the needle is a what kind of pole? Remember, opposites attract, North Pole and South Pole attract, so if the red needle is attracted to the South Pole, it must be north. All right, now it says place the compass in the middle of the screen and position the bar magnet so that the South Pole is right underneath. Okay, and now I'm going to quickly slide the magnet to the right. Oh, that's not very quick. We got stuck here. Yeah, I'll try it again. Okay. And notice how quickly the needle changes. There's a little bit of lag time there, but it reacts pretty quickly. Right, now I'm going to move the magnet all the way down to the bottom here. And I'm going to do the same thing. I have the South Pole directly underneath, and I'm going to slide it to the right. And notice how the needle changes. In particular, notice how fast the needle moves in response to the magnet. Did it take, this is number 13, did it take longer for the needle to move the second time with the magnet all the way down here? Yeah, I'd say so. Number 14, why does the compass needle move differently when the magnet is farther away from the compass? Think back to what we learned about electric charges and the strength of the electric field around the charge and how distance affects the strength of that field. You'll find that magnetic fields are very similar. The farther away from the magnet, the weaker the magnetic field strength is. So number 15 is related to this. Note the brightness of all the tiny needles showing the magnetic field. So all these tiny little compass needles, those are there to show you the direction and the strength of the magnetic field. And the way it shows magnetic field is the brightness, or how highlighted the little compass needles are. So number 16, why are some needles brighter than others? Why do you think these compass needles right here, really close to the magnet, are brighter than these, say, way over in the corner, very far away from the magnet? Okay, now I'm going to flip the polarity back again. And I'm going to click this setting over here that says See Inside Magnet. And what's going to show up here is a bunch of little compass needles inside the magnet. Number 17 asks, how are the tiny compass needles that show the magnetic field inside the bar magnet aligned? In other words, in what direction are all of the red North Pole ends of the compass needles pointing? Are they pointing toward the North Pole or toward the South Pole? So for number 18, you're going to have to think back to what you learned about electric charges and positive and negative charges and how they repel each other, how they act at a distance from each other without ever touching, and how they interact in terms of field strength and distance, and see if any of those qualities of the charges and the electric field around each charge apply here with magnets and the magnetic strength of north and south poles, and how the north and south poles interact, and how distance affects the strength of a magnetic field. Those are the types of things I'm looking for here with number 18. How magnetism with a compass needle are similar to test charges in electricity. Okay, now I'm going to click on Show Planet Earth. And what we have here is a giant globe with a big magnet inside. Okay, and here we have North America up here. So this is the North Pole. We have South America down here in the South Pole. And question 19 asks, where is the North Pole, the magnetic north, of the compass pointing? So let me move the compass around. Okay, so the North Pole of this compass needle, where's that pointing? So because this is a North Pole, what is Earth's magnetic pole here at the North Pole? It isn't north at all, is it? It's actually south because it's attracting the North Pole of this magnet on the compass needle. Okay, now I'm going to click Reset All. Yes, we want to reset all the settings. And I'm going to check this little box that's going to bring up a field meter. Okay. Now this shows the magnetic field strength around a magnet, which is called the B field. And we're just going to look at this top one here. We're not going to look at these different dimensions. Remember, magnetic field, just like electric fields, extend out around an object in all three-dimensional spaces. So we have different axes. But we're just going to look right now at this top measurement here, the B field measured in Gauss. These G here are the units. Those show that these are in units of Gauss. And I'm just going to move this meter around and watch that top line there and see how things change. Wow, it really jumps up when I go right over the top. And we can go all around near the end. Let's go right to the middle. Let's go farther away. Question 21 asks, does the field increase or decrease as you move the meter closer to the magnet? Okay. Now we'll get further away. See how that magnetic field is changing. Now I'm going to move the meter the same distance away. Oh, let's see. I'm sorry, we're supposed to move it about 1 inch to the right. Okay, question number 22. What is the magnetic field strength in Gauss about 1 inch away from the north end of the magnet? So looks like about 2.3. And then we're going to move it to the same location. I'm just going to estimate. That looks close enough. And the question is, what is the magnetic field strength about the same distance away from the South Pole? That's question number 23. Is it about the same or is it different? 2.38. That's pretty close to the same. Okay, now we're on the back page of the worksheet. At the top left of the simulation window, click Electromagnet. So I'm going to go up here and click on this tab here, and it's going to bring up this electromagnet. Here we have a battery with a potential difference of 10 volts that is pushing this flow of electrons through this wire. And we're going to take our compass and just move it around. This down here is actually the electromagnet part. The battery itself is not magnetized, but these wires, as you can see as I move the compass around, are magnetized because they attract different ends of the compass needle. So number 24 says, is the left side of the electromagnet the north end or the south end? Okay, so take a look at your compass needle. Which end of the compass needle is being attracted to our electromagnet on the left side here? Remember, the red is the north end, so this side of the magnet must be the South Pole. Okay, and we're going to bring up our field meter again. I'm going to move this field meter around. Again, just look at that top B field. See how strong it is right on top. And then it goes down. Farther away I get. Does the field strength increase or decrease as you move closer to the magnet? Well, I'm going to move it farther away. And it looks like the field strength is decreasing as we get farther away. All right, now we're going to put our field meter right on top of our solenoid, those looped wires. And you'll notice over here I can adjust the loops, the number of loops, and so using the top line, the B field strength in Gauss, you need to fill out that table on your worksheet. So with 4 loops, we have a Gauss or a magnetic field strength of 300 Gauss. Now if we drop it down to 3 loops, your solenoid only has 3 loops now, the field strength lowers to 225. So in that table on page 4, this is kind of in between number 25 and 26. So number of loops is 3, so in your table there put 225. Now we're going to drop it down to 2. When we have 2 loops, we only have a field strength of 150 Gauss. And for 1 loop, we now have a field strength of 75 Gauss. So number 26, based on your data, does the magnetic field strength increase or decrease as you increase the number of loops in an electromagnet? So look at your table that you filled out and make an inference based on your data. Now we're going to increase our loops back up to 4, and then we're going to play with the voltage a little bit up here. We have a little slider bar that lets us decrease our voltage, so I'm going to put the voltage all the way down to 0. And notice that when we get to 0, all of the little compass magnets, they disappear because no electricity running through those wires means there is no magnetic field. There's no electromagnet because the electrons are not moving anymore. So the voltage, when the voltage is 0, the field strength is 0 as well. If we increase our voltage to 2 volts, we have a field strength of 60. So you want to record that in your data table there on your worksheet. With a voltage of 4, we jump up to a field strength of 120 Gauss. We're going to move it up to 6. Oop, I went too far. Okay, at 6 volts we have 180 Gauss. And at 8 volts we have 240 Gauss. And then finally, all the way up at 10, we are back up to 300 Gauss for our field strength. So question 27 asks, what happens to the electrons, these little dots that are moving through the coils, when you decrease the voltage? I'll go ahead and decrease it, and you can see what happens. Now, I can reverse the polarity of the battery, just for fun. Notice what happens to our compass when we switch polarity. Switches the polarity of our electromagnet. All right, in 28, based on your data above, what is the relationship between voltage and field strength in an electromagnet? So look at your data in your table there and make an inference based on how the field strength changed with the difference in voltage. And then give some thought into how you can change the strength of an electromagnet. There are several different things you can change in order to get the exact magnetic strength that you like or need for whatever application you're using it for, whether it's electric door locks in a car or a doorbell or all sorts of different moving parts applications and different appliances and electronic things. Okay, so you should have everything filled out on your worksheet now, and hopefully you can get that all finished and turned in next week.